Geometric series. We've done arithmetic series in C1, and now we're looking at geometric series in C2. So here's a geometric series. Can you see how to get from one term to the next here?
Excuse me, we're multiplied by 2.
Yeah, so instead of adding, we're now with arithmetic series, we're timesing. So similar notation, we use A for the first term, and we now have not a common difference, but a common ratio. So that's what we're timesing by to get from one to the next, and that's R, and then N for the number of terms. So you might want to go back and watch the AS video, arithmetic series video again, because this is going to be really similar. We're going to work out what's going on. So we've got A here, then we've got A times R, then we've got A times R times R, then we've got A times R times R times R. So this one is going to be A times R times R times R times R, and it's very similar to arithmetic series. To get the first term, we don't times by R at all. Second term, 1R. Third term, 2 R's. Fourth term, 3 R's. Always one less than the number of terms. Okay?
Yeah.
So here, A R to the don't know equals 256.
Yeah.
We know that A is 2.
2. Yeah.
We know that R is 2. So 2 to the don't know is 128.
28, yeah.
So 2 to the what is 128?
6, 7, 6, 6 or 7? Yeah.
To be honest, we could use logs to solve it, couldn't we? But let's see if you're right. 2 to the 6 is 64. 2 to the 7 is 128. 2 to the 7 is 128. So this must be that.
Which is the
Eighth term, exactly. So the 8th term is 256, which is AR to the 7. And we can do the same thing over here to work out how many terms there are. So AR to the n minus 1, that's the nth term, is 32768. I think we'll have to use logs for this one. We know A is 2, we know R is 2. So 2 to the n minus 1 is 6, 1 and 6. What's half of 32768?
16384.
4. Okay, so n minus 1, opposite of 2 to the power of is log to base 2. So log to base 2 of 16384, which is... Oh yeah, it's in that funny place again. Option F6. Yeah, there it is.
F6.
Option calc F6.
F6.
F4,
Okay.
yeah. And then 2, comma, 16384.
16384. 14.
So n is 15. So the number of terms here is 15. That's the 15th term. There. So it would be AR to the 14. Okay? So, what did we look at next? Adding them up? Yeah. What do they all add up to? Do you remember we had a clever trick before? We're going to have another clever trick.
Yeah.
So we're going to have 2 plus 4 plus 8 plus 16 plus blah 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 plus, what was the one before that? 1, 6,
16384.
8, 4. Okay. Now, the clever trick we're going to do here is to times everything by 2. And I'm not timesing everything by 2 randomly. I'm timesing everything by 2 because that's what the common ratio is. Okay? So 2 lots of x is 4 and 8. And can you see I'm making something match up here? So I'm timesing everything by 2. I don't know what that times 2 is.
8 times 2 is 65536.
Okay. And now what I'm going to do is do this one minus this one.
Yeah.
Okay? Now, what that means I'm going to end up with is this one here having that taken off it.
Yeah.
And this one having that taken off it. And this 16 minus this 16. And this 8 minus this 8. And this 4 minus this 4. So all of this is going to be gone. in the subtraction, and I will end up with 65536 minus 2.
Yes.
Okay? So 2s, take away s, which is s, is 65534. And I didn't even need a calculator to add up all of that, which is pretty cool, I think. So, in general, what does that mean for a formula? Well, we say that the sum is equal to a plus ar plus ar squared plus blah 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 plus ar to the, well, the last term is ar to the n minus 1, so this would be ar to the n minus 2.
Yeah.
Okay, now I times everything by the common ratio r. So this becomes ar, this becomes ar squared, this becomes ar cubed, this becomes ar to the n minus 1, and this becomes ar to the n. They all get one bigger. And then I subtracted, I did this one minus this one. rs minus s equals, so this one cancelled this one cancelled this one, this one cancelled this one, this one cancelled this one, this one cancelled this one.
Yeah.
And all I'm left with is ar to the n minus a. Okay?
What happens then if r is bigger than 2?
Oh, it doesn't matter. Could be anything. I've just
So it doesn't matter that you might end up be left with.
two lots of s. No,
Yeah.
no, no.
Okay.
It's literally just r lots of s, take away s.
Okay.
And so what I can do is pull out s. And here I can pull out a. And then I can put that underneath there.
So that is the sum, isn't it? When you
Yep.
divide- Yeah.
Yep,
Okay.
that's the sum. Now actually I prefer it, it's exactly the same. If you multiply top and bottom by minus 1, then you end up with a 1 minus r to the n over 1 minus r.
Yeah.
And the reason I like that is that with a geometry, so this is how I would remember it. And the only difference there actually is if I go back and do this proof, but instead of doing this minus this, I'll do it the other way around.
Yeah.
Yeah? So I'll just show you just so that you know what's going on. Also, reminder, you do need to memorise this proof because it can come up in the exam and it's worth about half a grand. So, a plus ar squared plus blah 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 plus ar to the n minus 2 plus last term ar to the n minus 1 times everything by ar plus ar squared plus ar cubed plus blah 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 plus ar to the n minus 1 plus ar to the n. Then do this one, take away this one. Okay? So now this is cancelling with this is cancelling, this is cancelling, this is cancelling, this is cancelling, and we end up with a minus ar to the n, factor out the s, factor out the a, divide that under there, and you get that.
Yeah.
Okay? Now this is the sum of the first n terms. Okay?
Mm-hmm.
Now, if r is close to 0, so between minus 1 and 1, if that, then you can actually, what r is doing is, for example, say r was a half, it's halving it, halving it, halving it, halving it each time. Each next term the sequence is half as big, so they get tiny, 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 tiny.
It is, yeah.
And then what you can do is just keep adding them up literally to infinity, and you never get past a particular number. So even though you're adding and adding and adding and adding to infinity, infinitely many times, the thing you're adding on gets so tiny that it doesn't make any difference, or it makes insignificant difference. And then that formula, the sum to infinity, is the same as the sum to n, but you don't need that fraction on the top. So it's a nice way of remembering it. A, instead of having a 1 minus r to the n over 1 minus r, you just have a over 1 minus r. So that's why I prefer that formula that way round rather than r to the n minus 1 over r minus 1. I prefer it this way round. So we've actually got 3 formulas to learn. The nth term, a r to the n minus 1. The sum of the first n terms, a 1 minus r to the n over 1 minus r. and the sum to infinitely many terms, provided r is between -1 and 1, then this equals the same as the formula above, but without the fraction on without the bracket on the top. That, yeah. So, same thing happens with arithmetic series, recurrence relations, sigma notation. Students just get all muddled, and what we need to do is translate the information. So if it says the nth term is y, you write down ar to the n minus 1 is y. You write maths, not words. If it says the sum of the first n terms is y, you write a 1 minus r to the n over 1 minus r is y. So you write it as a formula. If it says the sum to infinitely many terms is y, then you know that a over 1 minus r is y. You get the formula. Then you can do simultaneous equations. So, you've got your notes. Pause the video. Try and translate these same, or very similar to the arithmetic series, but now geometric series. Pause the video, have a go, and then we'll go through the solutions. So, here we go.
Okay.
The fifth term.
So we're doing AR to the n minus 1, and n in this case is 5, so AR to the 4,
Yeah.
11.
Perfect.
8th term is 7, so AR to the 7 is 7.
Yeah.
The sum of the first 8 terms is 12. So we're doing a sum. So we're doing A 1 minus R to the n,
Yeah.
but we know that it's n is 8.
Yeah. That's it.
Over 1 minus R is 12.
Yeah.
Sum of infinite terms is minus 2. So A over 1 minus R is minus 2.
Yeah.
The 12th term, AR to the 11,
Excellent.
is minus 17.
Perfect. That's it. Next.
Sum of the first 9 terms, so that's A 1 minus R to the 9,
Yeah.
is 1 minus R is equal to 15.
Yeah.
The 17th term, so AR to the 16, is 91. Sum of infinite terms, so A 1 minus R is 500.
Yeah.
AR to the 10 is 9.
Yeah.
And 1 minus, A is 1 minus R to the 6.
Yeah.
Or 1 minus R is minus 20.
Perfect. And then, same as arithmetic series, what you'll end up with is 2 of these, and then you do simultaneous equations. That's the hard bit.